the authors of the book. That comes from Morrison Hasteller. All right, so we got our new way, the shell method, an alternate way to do revolution solids. So if it's, you can either slice, so that would be perpendicular to the axis of revolution, or you can wrap around the axis of revolution in layers, and that's the shell method. And then the strip would be parallel to the axis of revolution. So that gives you some flexibility on what kind of strips you can use, which is nice. And then, of course, these on the base, you just, the strip is one part of these different things, okay? All right, so if we look here, here was number 4. So if you're wrapping around here, you're going to have a strip that's here, like so. So your H is going to be, what was this right x coordinate? 4 minus, what was this line? Y equals 2 minus x. So it'd be x equals 2 minus y also, right? It'd be 4 minus 2 minus y. And then the P would be what? 0. It's always top minus bottom. So your strip is right here at some y coordinate. It might be down here at -0.5, -1, -1.5. It's down here at some y coordinate. So it's top minus bottom, 0 minus y. Okay, so 2 pi and then h times p. And then the strips go from what? -2 to 0. So what was the answer on number 4? 8 pi over 3. Okay, next one, number 9. Not to spend too much time. If you have questions, 16 pi over 3. 16 pi over 3. We're good there. Okay. Again, what they drew the strip in for you, right? But if you're revolving around the y-axis, it's got to be a vertical strip. It's got to be, if you're doing the shell method, it's got to be parallel to the axis of revolution every time. So H would be this minus this, and the P would be x minus 0. X minus 0. Okay, number, what was the answer on 9? We said 16 pi over 3. Okay, number 12, pi halves. Did you split that into 2? You had to split that into 2, right? This is one. Now, so this would have been when maybe we talked about this. I can't remember, but this is one where you would rather not do shell, right? Excuse my voice, but you would rather not do shell here because shell would be horizontal strips because it's a horizontal axis revolution. You'd have to split it into 2. What you'd rather do, if you had your choice, you'd rather do that, right? You'd rather have a slice because it'd be a circle. There'd be an empty space. What was this graph? 1 over x squared. So your strip would be your radius. What's that? It's just 1 over x. So it'd be 1 over x minus 0, and it would just be pi r squared from 1 to 2. I mean, that would be a really easy one to just do a disk method, right? But you're supposed to do it with shell for practice, but that would be, if it was on the quiz, you had your choice, you definitely want to do that method on that one. Okay, 17. It was similar to what we did in class. 192 pi over 5. 192 pi over 5. And this one would be just about as easy either way. If you were going to do it'd be a washer, right? If you were going to do a washer, there's your big R and little r. Okay, so that'd be pretty easy. But if you're going to do a shell, right, your shell strip would be this way to be parallel. So the shell's pretty easy. Now, what's your P on that one? What was your P on that one? 6 minus x, because your strip is right here, x. So P would be 6 minus x. Okay, 21a. Oh, look at me. I'm not even getting the grade, and I got 4 pictures wrong. Okay, what'd you get for 21a? 128 pi over 7. So you're revolving around the x-axis. So you want to have a... Now, it said use either here, right? It said use either. So if you're going to do a shell, it'd be this way. So the red would be shell. What would be the H? Anybody do shell? 2 minus square root of y. Cube root. It is? Did I do the right problem? Is that 21? That's weird. Really? Oh, that's easy to fix. 2 minus cube root of y, and p would be y minus 0, right? And if you wanted to do this as a disk, it would be no empty space. That'd be pretty easy. The r would be x cubed minus 0. And then you would put it into there, right? Gosh, I can't believe I did that like that. I thought I typed this up before. I thought I've used this other years. I can't believe it. Okay. Anyway, so on this one, what did you do here? Shell, or did you do shell on all of them? You did some, okay. So like this one would be, if you were going to do shell on this one, it'd be vertical, right? Because you got a vertical axis. What was the answer on B? 64 pi over 5. So if you do shell on this one, you're going to have h is going to be x cubed minus 0. P is going to be x minus 0, right? If you did a washer, it would be, there would be big R and there would be little r. I just think it's good to practice those. Big R would be 2 minus 0, and little r would be cube root of y minus 0, like that. So I think it's just good to make sure you can do both ways on that. Okay, C. 96 pi over 5, so now we're revolving around here, so this is that, x is equal to cube root of 1. So now revolving around there, so if we were going to do a shell, again, vertical strip, so the h would be x cubed minus 0, the p would be, what would p be here? 4 minus x, right? 4 minus x right here. And then if we were going to do washer, it would be a washer because it would be empty space. You'd have big R would be there, little r would be there. So big R would be 4 minus cube root of y, and little r would be 4 minus 2, right? Okay. And then what was T? 320 pi over 7. 320 pi over 7. So we've got, let's see, shell would be this way, right? Shell would be that way. So the h would be 2 minus cube root of y. And the p would be 8 minus y. So here would be the y, and here would be your strip, 8 minus y. Or we could do washer. Big R would go all the way to there, little r would go to there. So big R would be 8 minus 0, and little r would be 8 minus what, x cubed? 8 minus x cubed. Right? So set it up either way, 320 pounds. Okay, good. All right, moving on. Moving on, get your notes out. Get your notes out. We're in physics. Physics couldn't exist without calculus. Oh, you could do some basic physics. Physics wouldn't exist without math. Math couldn't exist without physics. Physics could not exist without math.
You could be like a
Could I?
you think you could do like a forensic application? Like analyze like crime scenes.
I like it. I like those. You think class like that?
It's like chem, biology.
Not for me.
What part were you? The chem with bio.
What?
That's the what part of it.
Like
Yes, this is an idea from physics, the concept of work, to do work. Now, the concept of work, the basic formula for work is force times distance. Okay? Force times distance. So, the key is there has to be a force, which for us is typically weight. You think the force is measured in pounds. So, a lot of times in these problems, you can think of it as being kind of equivalent to weight. Okay? It's technically not just that, but you take that. And there has to be a distance involved. If I stand here and hold this above my head, I'm not doing any work right now by the definition of work. And if this was really heavy, if this was like 150 pounds, and I would, my arms were shaking and it was really hard to do, I'm still not doing any work because I'm not moving it through the distance. Now, getting it to that point, that was work. So if I lift a 10-pound book 7 feet off the ground, that would take 70 foot-pounds of work. So if I had a 10-pound book on the ground, picked it up, lifted it up here, the process of moving that to that spot, that's work, 70 foot-pounds, and that's what we call the units. Now, in physics class, you probably use metric units. What were the units for work? Have you guys been in physics? You were in physics? Newton meters. Newton, typically force in metric is newtons, and then the distance unit would be typically meters, Newton meters. Now that also had a name too, I think. Is that joules? Is it Newton meters? Newton. Well, that's a different version of joules. Yeah. Because, what?
A watt times something.
I think it's like, it doesn't matter because we're going to do all ours in foot pounds or inch pounds.
Or
1 Newton meter. Yeah. Is equal to energy transferred or work done on an object. Okay, so Newton meters or joules, but we won't use those terms. It's kind of like ounces, right? 16 ounces in a pound, is that right? So that can be a unit of weight, but it can also be a unit of volume, right? Ounces, so maybe joules in different categories, but because it did mention energy in there. So it's force times distance. So for us, it could be like foot pounds or inch pounds, depending what our distance unit is. But our force unit and all the problems we use can be pounds. Now we're just going to scratch the surface on this. You notice in our packets we haven't had any work problems because it's not on the AP test, but it is, something you do need one that's kind of that thing just beyond what the AP test might be on. But we're gonna do it. So it's another application of an integral. Now, why do you need the integral? It seems pretty simple. You just take how far you do it either way. Well, technically, and this is the difference between a high school physics course and a calculus-based physics course. And that is, if you take and lift a 10-pound book from the floor up to 7 feet, technically, the book does not weigh as much in one of those two spots. Where does the book weigh more? Closer to the ground, closer to the center of the earth, right? The farther you get away from the center of the earth, the less things weigh, because it's based on gravity, right? Now, in 7 feet, the difference is so negligible that we can ignore it, and we actually will ignore it even in calculus. But there are some things that we're not going to ignore. Again, the difference between calculus and non-calculus based mathematics is the change, the rate of change, right? And that's what calculus is all about, okay? And so we're going to get into some problems, and I'll show you how they would differ in a high school physics kind of setting versus a calculus based. But this would be a situation where we would ignore that difference. We're going to ignore that difference. it's so minuscule, right? But what we're saying then, so where the calculus part comes into this, is when I take that 10-pound book and I lift it 7 feet off the ground, I've got a changing weight, right? Kind of like when I slice the lemon. With each slice, right, what's changing? The radius of that slice is changing, right? And if I slice it really thin, so as I slice, the radius is changing. So we have an equation for the radius. So that's exactly what we just had right here, right? The radius is 8 minus x cubed. It depends where the strip is, right? It depends where the strip is. So we set up an integral to add up all those little pieces, add up all those slices. Well, what we'd be doing in this case is we'd be saying, okay, the book weighs 10 pounds on the floor, and if I raise it up about an inch, now it weighs whatever, let's say 9.9. It's not that much difference, but let's say it's 9.9. So now let's figure out how much work we did right there. Now that's still an approximation, right? So if we say, okay, between 10, so 1 inch, if we raise it 1 inch, we just did, it was 10 pounds at the beginning, it was 9.9 at the end, so let's average that. And let's see how much work we did that one. Do you see how that's like doing the volume of one slice of lemon? Remember when we did the radius, we averaged the radius on each side, right? We said there's the volume of that slice. And then we added the next slice, the next slice. So if we went 1 inch at a time, right, we can add up how much work we did each of those. But even then, the amount of work was changing because it was 10 pounds at the start of that inch and it was less pounds at the end of that inch, right? So we could kind of average it. Well, how could we make it better? Do a ½ inch at a time, right? Raise that book a ½ inch at a time, and then see, and then 1/4 of an inch. And you see where we're going with this? And so infinitely, because the amount of pounds is changing each time. The amount of pounds is changing each time, the force. So we're doing smaller and smaller slices. So basically, what we're saying is we're gonna want to calculate all those little bits of work that we're doing as the pounds is changing as we lift it, and let the integral add it all up. So we've got a changing quantity that whole time, just like the radius was changing with all the slices, and the integral is going to add that up. Okay, so what's going to become the dx? In that scenario, what's going to become the dx, the little piece that goes to nothing? Not what? The distance you move each time. So right here, in that scenario, this is going to become the dx, right? Because the distance is going to get narrower and narrower, those slices of distance. Now, in some of our examples, we're going to do it will be something else that will become the dx, and we'll see. Okay, so we're just going to have about 3 different examples, and really only 2 of those that I'm going to require you to do in the quiz, but we're going to talk about that. Okay, the first one here is Hooke's Law. Okay. Well, right, yeah, there are some things you can look up of how the effect of gravity, right, but it would go out. It would go out many decimal places and get the scientific notation and stuff like that. There might even be an example of some of that up there. I think there's an example in the book about working against gravity. And so if you're interested in that, you can read about it on page 434, 435. I don't want to get into that. So we're going to talk about Hooke's Law, which is the force required to stretch or compress a spring. Now, when we talk about a spring, we got to think about something more than like a slinky or something like that. But matter of fact, we're gonna think of this spring as being attached. Think of the spring as being attached on one end. So let's say we have a spring attached to the wall on one end. We were going to pull it out. We were going to compress it. Okay. So Hooke's Law says the force is proportional to the length that it's stretched or compressed, right? So the more force, so think about a spring. So at the beginning, it might be kind of easy to stretch it, right? But then it gets harder and harder and harder, right? It requires more force. So the farther out it's stretched, the more force it requires. So if you have a spring that was a natural length of 3 feet, okay? Stretching it, so for this particular spring, the K is called the spring constant for that particular spring. So some springs will be thicker and harder to pull, and some might be thinner and easier to pull. So if I had a spring that was a natural length 3 feet, and I wanted to stretch it to 5 feet, and that took 10 pounds of force, what would the K be? Well, real easy. 10 equals K times key is, so very important to understand this part of it. The X is how far you stretch the spring, not the length of the spring, right? So when we stretch it to 5 feet, we've moved it 2 feet, right? So it's always got a natural length. The spring has a natural length. And then where do we move it to? So you got to read the question carefully. It's either going to say you stretch it to 5 feet or you stretch it 5 feet. See how those are different? If you stretch it 5 feet, it means you went from 3 to 8, right? Then you would put a 5 in for the X. But if you stretch it to 5 feet, it means it was 3, now it's 5, you stretched it 2. That's the number we want. Okay, so for that spring, K would be 5. So for that spring, its force equation would be F equals 5X. Okay? All right. So the question then is how much work was done stretching that spring 2 feet? Well, for that, this would be the pounds. And like we said, this would be the feet. And that's how we get our foot pounds. Because, so spring problems are the easiest ones of all. So you just got to get that force equation, which is just from Hooke's law, F equals K times X. So it's always going to be 5X, 10X, 2X, 12X, something like that. So you're going to find that K value based on the given information, and you're going to throw that in. Now, that'll give you how much work. Because again, think how much, what's happening. As we pull that spring from 3 feet, as we pull that spring, it gets harder and harder, harder and harder, right? So if we pull it 1 inch, it was easier at the beginning of that inch than it was at the end of that inch. And it was changing in between. So we could do 1 inch and figure out how much work we did, 1 inch, how much work, and then add up all the bits of work. But a better approximation would be ½ inch at a time or ¼ inch at a time, right? Just like the slices, okay? So what we're doing is we're wanting to make those thinner and thinner. We're wanting the feet, the distance part of that, to go to nothing as we add up the bits of work. And then what would be the A and the B here? 0 and 2. Because how much work would there be to not move it at all? No work, right? And so so these numbers have to be the amount of stretch. Okay? So 0 to 2 is what you want. Okay, so the natural length, if the spring is at its natural length. So if we took this same spring, so it would still have the equation 5x, but we did the integral 3 to 5. What would that mean? So here's this spring. It's attached to the wall. There's its natural length of 3. That's right. So if we stretch it to 5, right, there's 2 more, right? That would be 0 to 2. But if we said 3 to 5, that would actually be stretching it from a length of 6 to a length of 8, right? So its natural length was 3, and we stretched it out to 6, and then we said, okay, now we've stretched it out to 6. How much work is done to stretch it 2 more feet, right? There we went from a stretch of 3 to a stretch of 5, and then our interval would be 3 to 5, and that would be bigger. So put that in your calculator. Just put that in your calculator real quick. How much work is it? And we would think that would take more work, right? That should take more work because it's harder the farther you get it out. In both cases, we're stretching it 2 feet, but the second one should take more work. So 0 to 2 is what? 10? Okay, when you do that integral. And then, what's 3 to 5? 40, right? And that would make sense, okay? So 10 foot-pounds of work are required, 40 on the other. Okay, both cases we're stretching at 2 feet. All right, so that's pretty simple. That is for a spring. Okay, that's the work done to stretch a spring. All right, so and it's a linear relationship, so it probably could be figured out. You could figure it out without calculus, because when you average in there, right, you could since it's linear, you could come up with that as well. But anyway, it's a pretty simple example, and you can see how we get foot-pounds out of our problem. All right, so here's the next one. Rope in a bucket. A 5-pound bucket with 2 gallons of water. Let me, I have a PowerPoint here, but I'm not sure. Let me go through this and see if I'm missing anything here. It's got pretty good pictures. Okay, so here's their example. Spring has a natural length of 1 meter. They use newtons and meters. 24 newtons stretches it to 1.8. So your X would be 0.8. Okay, so your X would be 0.8, your 24 is there, and so you get K is 30. So that means your force equation is 30X. How much work is needed to stretch it 3 meters beyond its natural length? So what would your integral be from here? 0 to 3. So it's just you got to make sure you read the problem and understand what those numbers mean, and then they actually work it out. Okay, so that's Newton meters. Okay, over a very short distance, even a non-constant force doesn't change much. So that's where we add up the small bits of work. Okay, so now we're talking about this bucket problem. So let's go back to my example. We'll come back to this picture if it's helpful. Okay, so I got a 5-pound bucket with 2 gallons of water, and I'm going to raise it 20 feet. Okay, so write this down if you want to. There's 3 types of problems we're going to do, and for sure 2 of those you're going to have to be able to do in a quiz. A spring problem, and a rope and a bucket problem. Okay, so rope and bucket problem is another type. So we're going to narrow this down a little bit. It's kind of like related rates, but I didn't tell you which related rate type of problem we did. You know, we did sand on a pile, and we did a lot of different related rate problems. Here I'm going to be more specific in the type of problem. You got a 5-pound bucket, 2 gallons of water. So like in a well, maybe, right? You got it in a well, and there's rope attached to the bucket, obviously. So the 20 feet of rope weighs 1.6 pounds. How much work is done in raising the bucket? Now, in physics class, you would say, oh, okay, I'm just going to take 5 pounds. I got to figure out how much water weighs. Well, in your book, it depends. I think they use something different on the slideshow than we do here. They say in your, and that would be density, right? That's a term you've seen in physics. Water is, I think in our book, I would give you this number. Let's use this number here. Okay, 62.4 pounds per cubic foot. That's how much water weighs. Okay. So you have that's cubic. That's not a gallon. Let's see what they say on this PowerPoint. I think they do gallons? 16 pounds. 8 pounds to a gallon. Okay, so let's go back here, and it's 8 pounds per gallon. So I would give you those. Okay, so we got 16 pounds of water in the bucket. The bucket weighs 5 pounds, so we got 21 pounds, right? So in physics class, you'd say, okay, we got 21 pounds, and we're going to raise it how far? Times 20 feet. So that's going to be 420 foot-pounds. Now, what is that not taking into consideration? Change in weight of gravity, but we're going to ignore that because that is so minuscule. So we are going to ignore that. The weight of the rope. When I take, so that bucket's down in the well, 20 feet of rope, and I lift, say, a foot out of there, whatever, right? And then I lift again. On my second lift, I'm pulling up less rope, right? Some of the rope's laying over here on the ground. And now I might only be pulling up 16 feet of rope, right, on the next pull. And on the next pull, I might only be lifting 10 feet of rope or whatever, right? So now, if it was attached to a pulley and you were just cranking, right, now it'd be a continuous change, right? So as you go, right, you're pulling up less and less rope, right? You're pulling up less and less rope. Now, in physics class, you would probably ignore it. You would probably ignore the weight of the rope, and you would just work on the body, okay? But we're not going to ignore the weight of the rope, so we're going to figure that in. So, how do we do this? We're going to want to, well, let's go back to the PowerPoint here. They do it a little bit differently, how they set it up. I'm going to show you how I think is a good way to set it up. Okay, so theirs is pretty similar here. It says 0.08 pounds per foot. Now, what's 0.08 times 20? What's 0.08 times 20? 1.6. Okay, so you see the difference in how I worded the problem and how they worded the problem. I said the 20 feet of rope weighs 1.6 pounds. They said the rope weighs 0.08 pounds per foot. Same thing. So you just have to be able to handle either situation. Okay? So if they give it to you this way, you can use that, or you can use what I have. Okay? And the bucket starts with 2 gallons of water, and it says it's empty when it reaches the top. So the bucket is leaking. Now, I'm not going to do the leaking bucket in my example. We'll come back and do that here in a second. Okay? So let's first work it where we're just raising this bucket of water. Okay? So here's how this looks. We're going to do our integral. And we need to add up, and again, the dx is going to be our feet. Okay? Dx is going to be the feet. So all we need to add up here, all we need to have in here is what? Pounds. So we need pounds. So we just need the weight, but we got 3 things. We got the bucket, we got the water, and we got the rope. We got to get all 3 of those added up. Okay? So those all weigh something. Now, the bucket and water aren't going to change, but the rope is. Right? So there's going to be an equation in there for the rope. I'm not going to show you how to get that equation. So the bucket is 5 pounds, not going to change except for gravity, and we're going to ignore that. Plus the water, 16 pounds, right? The water is going to weigh 16 pounds. And now the rope. It's not 0.08x. Okay, when we draw this picture, okay, here's the bucket down here. This is going to be 0. This is going to be 20. Okay, and the bucket is right down here, whatever. This amount of rope, let's call that x. We could call it y, actually, since it's going up and down. We could call it y. It might make more sense, but we'll call it x. That's fine. Okay, how much rope is out at any time? If you do 0.08x, it's going to be 0.08 times 20 minus x, right? Because what is this length right here? If we call, I'm sorry, we're not calling this length x. We're calling the bucket, kind of like the strip, kind of like the P. We're saying x is here at some, the bucket is at some x value. When it's down here, it's at 0, right? And when it's all the way up here, it's at 20. So it's going to be 0.08 times 20 minus x. Now, some people have trouble coming up with that equation on their own. Okay, so think about it. What we've pulled, because remember, 0 or x is going to be how far we've lifted, right? So when it's down here, we haven't lifted at all. Okay, so when we haven't lifted at all, how much rope do we have? We have 0.08 times 20, right? So when x is 0, we want to have 0.08 times 20. If we did 0.08x, that would be a problem, right? When x is 20, we want to have, there's no rope left. When we've pulled it all the way up, 20 feet, there's no rope left. So we want 20 minus 20, which is 0. Now, here's how so that's exactly right. It's gonna be 0.08 times 20 minus X. And it's always gonna be a linear situation. When we do a rope and a bucket, it's gonna, it's gonna lose so many pounds per foot, because the rope's gonna be the same thickness all the way through, and it's gonna change like that. And then, what would be our interval here? 0 to 20, because we're lifting it the number of feet. So this is all pounds, so these three are all pounds, and this is feet, so that you can split them. Okay, so 0 to 20. All right, go ahead and type that in and see what you get. Then I'm going to show you here another way you could have done that. You got this equation. Okay. And it's gonna be more helpful. It's probably going to be more helpful in the leaky bucket one. What do you get? 436. Exactly. Yeah, foot-pounds. Okay. Now, let me show you. So we got the 0.08 because I showed you the PowerPoint, right? And it said 0.08 pounds per foot, right? Now, you could have got that here by dividing here, but here's, I think, an easy way to get this. So if you know that you've got 20 feet of rope that weighs 2.6 pounds, here's what I would make it a little XY table. This is going to be feet. This is going to be pounds. Okay? And I would say, okay, when I've pulled up 0 feet of rope, how much does the rope weigh? 1.6. When I've pulled up all 20 feet of rope, I have 0 pounds. Now just do it like a line equation. You got 2 points, right? So now all you need to do is go y equals, which is your pounds, right? Y is your pounds. So you always want y to be pounds, x to be feet. So y equals, now you do your slope calculation. So 0 minus 1.6 over 20 minus 0. So that becomes out to negative 0.08, right? So you get negative 0.08 is your slope. And then x minus, and then you just pick one of these, right? Well, I would pick the y, that one's an easier one. So look what we get. We get y equals negative 0.08x plus 1.6. So right here, you could put negative 0.08x plus 1.6. You could put that right here. Now, isn't that the same thing? You take 0.08 times 20, that's 1.6. 0.08 times negative x would be negative 0.08x. You get the same thing. I think over time, people found that a lot easier to do. Okay, so I got the rope, starts out at 0 feet pulled up, it weighs 1.6, and at the end, when I pull all 20 feet up, it weighs 0, do a slope calculation, and get your equation. Just do your line equation that we've used all year long, and then that'll give you that, instead of having to think through it. Either way is fine. Okay, 436 foot-pounds. Okay, now, let's say the bucket is leaking. And so now it's empty when it gets to the top. So now when you're pulling up, you're not only pulling up less rope, but you're pulling up less what? Pulling up less water. So now, what's our interval? Again, bucket, water, and rope. And then the dx is going to be our feet, right? And so all of this is going to be our pound. So how much does a bucket weigh? 5. We already know the rope was negative 0.08x plus 1.6, right? We already know the rope. Okay. So what's the water? Well, again, do exactly what we did here. Make an XY table, right? 0 feet pulled up. How many pounds of water do we have? 16. 20 feet of rope pulled up. 0. The beauty of this is it doesn't matter how much the bucket is. What if it says when the bucket got to the top, it was half full? So now you got 0, 16, you got 20 and 8, right? You'd have half of it. So now what do? We do a slope calculation, so 0 minus 16, 20 minus 0, that's negative 4/5, right? Which is negative 0.8 if you want to use it, okay? And so our pounds equation, or y equation, is negative 0.8. Yeah, I got a y-intercept over there, so it's on me, right? Negative 0.8x plus 16, right? Very much the same as this one, actually, it's coincidence, you know, it's decimal a little bit. So now the road and the water are both changing quantities. Okay, type that in your calculator. And then the integral will be from what to what? 0 to 20. So again, we're adding up these little bits of work, just like the book problem. The difference is in the spring problem, we needed the pounds of force, and that comes from Hooke's law, the Hooke's law equation. Okay, in the rope and bucket problem, we have to add up the bucket, the water, and the rope. The bucket, the water, and the rope. The rope is always going to be a changing quantity. The water will only be a changing quantity if it's leaking. How much? Oh, wow. Oops. Right, a lot less work, because as it came up, obviously you were going less. And then if we would have ignored the rope, what did we say it was? It was,
Well,
I was going to say that seems a little too low.
276.
Oh, too high. What'd you get?
I got 276.
276. You forget a parenthesis, or actually you don't need a parenthesis, but it's negative, it's just on this, not on the 16. So we had said, if you ignore the rope, it was 420 foot-pounds. But then we said it was 436 if you count the rope. Makes sense, because the rope weighs something, so that's going to make it more work. But then if the bucket's leaking, that's going to be less work because of that. Okay? All right, so those two we have to be able to do for sure. Okay? Here's the last one I want to do. Okay, the last one is this. So you're pumping liquid out of a tank. Okay? Now, so what changes here a little bit. So think of this like you're at a gas station. You're at a gas station and you go to fill your gas, right? And under the ground there's a tank. So think about this as being ground level right here. So under the ground there's a tank where they put all the gas, right? And you're going to pump it, so they want to know how much work is done. And the idea would be, okay, what kind of a motor? You know, a motor with so many horsepower can pump this much. It can do this much work, right? It can handle this load. So how many horsepower engine do we need to pump this water up to 4 feet above ground, which is where it comes out of the hose, right? That would be this kind of problem. Okay. So we got 10-foot deep tank full of liquid, right? So the way this works is we say, okay, how much work would be done to do one slab? How much work would be done to do one slab of liquid? Where that slab would get thinner and thinner and thinner. So you almost think of this like a slice, okay? And the thickness of the slice is going to be the dx. So that's going to be different than the distance. We're not going to talk about little bits of distance. We're going to figure out how much foot-pounds does it take to do one slab, and then we'll do an integral to add up all the slabs. Okay? All right, so what we need in this case is we need foot-pounds. We need foot-pounds to be what we get, or what our equation comes out to. Okay? So this particular liquid, let's say that it's water, and it's 62.4 pounds per cubic foot. Okay, so let's say we've got that. Okay, so we're gonna need our units to come out to be foot-pounds here. All right, now what is the volume of this one slice? What shape is that slice? That slice is a cylinder, right? So what is the volume of the cylinder? It's pi times the radius. What's the radius of this slice? 5. So that'd be feet, right? That's 5 feet, but it's squared. So pi times radius squared times, what's the height of that slice? That's going to be our dy. Okay? And that's going to be in feet also, right? So that's going to be one slab of water. But again, it'll get narrower and narrower and narrower. Okay? So there's our cubic feet right there. So far we got cubic feet. So if I put in here pi times 25, and then the dy I'm going to have go all the way over. Well, let's don't put the dy all the way over there yet, because I want to make sure my this all comes out. So this is going to be, this all here is going to be feet cubed. Right? Now what do I need? I need to multiply that by 62.4, because that is pounds per cubic foot, right? So that's going to cancel my cubic feet, right? So now I got pounds, and now I need feet. In other words, how far am I going to lift this slab? Well, again, let's label this slab as y, and how far do I have to lift it? No, it's not 4. This is 0 down here. This is 14. So what is this length right here? 14 minus y. Now you might be saying, now wait a minute, that liquid's going to go down to here, and then it's going to get pumped up to here, right? But this is offsetting right here, right? This is offsetting. There's no work. Because of the pressure, right? I mean, there's a lot of things going on, but because of the pressure of this, so as this fills up, that's going to push up to here, right? So if you filled this, you would get if you're here, and then that is like free, no work required. But then it's lifting it up above where it's at that it requires the work. Okay? So it's this slab is going to have to get lifted to here. Okay? All right. So 14 minus y is the feet. Okay, so look what we end up with. We end up with foot pounds. But the dy was a little different in this case. The dy was a little different in this case. It was part of this slab that we had, that we needed to do. So the dy, and then what is this going to be? From what to what? Now, okay, very good. Matt says 0 to 10.
0.
What I didn't tell you is how much water was in the tank. Let's assume the tank is full. This tank is full. Remember how we said the strips fill the space? What are we adding up? We're adding up all these slabs. Where are these slabs of water filling the space from? 0 to 10. What if there was only 8 feet in this tank? Wouldn't it make sense? If the tank's only half full, it's going to take less work to move all the water out of the tank. The tank's only half full, your integral only goes 0 to 5, right? So it's the strips. Think of these as like the strips. The strips fill the space from 0 to 10. So this would be 0 to 10. But if the tank was half full, it'd be 0 to 5. If the tank was only 8 feet full, it'd be 0 to 8. Okay? So it's the strips fill the space. So we multiply that all out. I think that's the same problem as, I don't know if they use 16. What they get on this one, they got 276. Yeah, they had 276. Okay, so here's their force is the weight of the water. The water at the bottom of the tank must be moved farther than the weight of water at the top. Okay, so, they use 62.5. They use 62.5, so there's a little different. Oh God, they go through all, there you go. Do you get something similar to that?
Yeah.
If you change your 62.4 to 62.5.
It's like 700 feet off.
Probably, because that's a big number. Change your 0.4 to 0.5 and then just double check. So a 1 horsepower pump rated at 550 foot-pounds per second could empty the tank in just under 14 minutes. So in other words, that would just be that divided by 550. What?
So people in my animal science class aren't as smart as the people in my AP calculus class. They don't even have a basic calculator for our animal science. Can we borrow two, please?
Borrow.
Thank you.
All right. Yeah, trust these animal science people. All right. So, okay. So that's the tank. Now, here's where this could get a little more tricky. Okay. Here, you don't have to write this down. We're not going to do this one. But what would be trickier about this one than the one we just did? The volume of the slab. Yeah, on the last one, the slab always had a radius of 5. Here, the slab is going to change. And so what you'd have to do is you'd have to get the equation. Well, what would you do? You would just do, let me show you what they do here. They put a y-axis in here. Okay? And so now what you need is this equation. So you just need this length. That'd be the radius. Right there would be the radius of your slab. So you need to write minus slab. So all you need is the equation of this line. So they go ahead and they do that. If that's, they said that it's 10 feet across, so that's 5. If we make this 0 down here, so that's 5/10. So that'd be x equals 2. That'd be a slope of 2. So it'd be y equals 2x. So the x equals 1/2 y. So this would be 1/2 y minus 0. And that'd be the radius. So now when we set it up, 1/2 y minus 0 squared. So it's pi times radius squared times your density, how many pounds per cubic feet, times your feet, your thickness. And then you would throw in the 10 minus y because you're going to have to lift it over the top of the rim. So if this strip is a y, then 10 minus y would be how far you're lifting it over the top, pumping it out of the tank. And so you have 10 minus y. And then the interval goes 0 to 8 because it only had, it's filled to within 2 feet of the top. So it's only, so you're only going to, the strips or the slabs that you're pumping are only from 0 to 8. Good question. This is some big, must be some big restaurant. They got a great big 10-foot tall tank of salad oil, like salad dressing.
It's like a chocolate fountain.
Well, yeah. And they got some mechanism, pumping it up over the top. Yeah, like the chocolate, there you go, like the chocolate fountain. Yeah. So it's a stream of salad. They've got
They
these.
go through all this work to find these crazy formulas, but they can't come up with a logical.
Well, there's probably, the gas station one is illogical. Problem, this one, this one's good. That one's gonna be interesting. All right. So, for your homework, for sure, what we need to be able to do is the rope and bucket. So the homework's going to be the spring and the rope and bucket problem. So it's the next one. It's in your book, 7.3. It's in your book, page 437. 1, 5, 6, 7, and 12.
What is our homework going to be for tomorrow?
Let's see. Shoot.
What do you guys do after first?
Yeah. Is that what you're leaving?
Probably. Still gonna start like.
Forgot.
No, not after essentially.
Well, I got some all day. So, I don't know if I'm going to be in here or not.
I think we'll probably
First, yeah. Are you going down to the Central? You're going to see
You guys
us.
have to go.
we have to go to class week.
And then you're leaving when?
I assume we're first. That's what we did last week.
And it seems like you guys might be leaving, I thought you were leaving earlier than that. I thought you were leaving like 9:15 or so, which means you're gonna need class at least till 9 or so. So you'll be able to get it. So.
Well, if we're not in class the day before, the day of, and the day after, yeah.
Well, like if you get, like if we had school tomorrow, if you went to Omaha and got home late, and didn't come to school.
We did a lecture.
What if you sick?
Well, it wasn't a lecture for most of us, it was mostly a lecture for, LD and,
I remember I was in the locker when we punched the locker. You know, that was scary. So they showed the first ball.
I don't think he didn't meet yet.
All right, here you go. I've got to figure out exactly